Ni hao. Hello. This is the 8th lesson in heat transfer. In the 8th lesson, we will look at engineering problems that involve steady-state, one-dimensional conduction heat transfer, and also generation of thermal energy. Remember that the generation of thermal energy occurs because some other form of energy is converted into thermal energy in the volume of the system that we are analyzing. Conversely, there may also be a conversion of thermal energy into some other form of energy within the volume of the system that we are studying. In the first part of the lesson, we will look at examples of relevant problems that fall into this category. And we will also discuss the need for a new technique to analyze problems of these types. By the end of this lesson, you should be able to provide an example of an engineering problem that fits in the category of the problem identified in the title of the lesson. By the end of the lesson, you should also be able to explain why problems in this category cannot be modeled using a thermal circuit, and instead require a new analysis technique called differential analysis. On with the lesson. Let's briefly review what it means to be steady state, one-dimensional, have constant properties, and have a non-zero thermal energy generation. In steady-state problems, there is no variation in temperature at any location in time. This is the definition of steady state. In a one-dimensional problem, there is a temperature gradient in only one direction. When properties are constant, it means that thermal conductivity and the heat transfer coefficients are all taken to be a single value and are not allowed to be variations in space, time, or temperature. Finally, when there is thermal energy generation, then the E dot gen term in the heat transfer energy balance equation is no longer zero. It must be included. This is the primary difference between problems that we consider in Lesson 8 and those that were considered in Lesson 7, the presence of a generation of thermal energy within the system of interest. Let's look at some examples of engineering problems that fall into this category. One example is the annealing of steel or other metal wires using electrical current. Annealing is a process of heating and cooling a material in order to make it stronger. When the annealing is done with an electric current, there is a thermal energy generation within the wire. Here is a picture of this process being done in a plant. Electrical energy is flown through the metallic wire, and due to the electric resistance of the wire, there is a generation of thermal energy that causes the wire to be heated. This is a sketch of the problem that you see in the picture. The wire is held between two holders. Current is passed through the wire, leading to a uniform generation of thermal energy within the wire. That generation rate is given by I squared times the electrical resistance, R sub E. I is the electric current, R sub E is the electric resistance. This is the total rate of generation of thermal energy. The volumetric rate is the rate divided by the volume of the wire. It has units of watt per cubic meter. This is one example where electrical energy is being converted into thermal energy. Another example would be systems that include an exothermic chemical reaction that converts chemical energy to thermal energy, or an endothermic reaction that converts thermal energy to chemical energy. Here is a match. A match uses an exothermic chemical reaction, the combustion of the material, in order to produce thermal energy. When you look at the temperature distribution along the length of the match, one might be able to analyze this with steady state or quasi-steady state conduction heat transfer. Another example of an exothermic chemical reaction are packets that can be broken to warm your hands. Here, chemical reaction occurs within the plastic that generates thermal energy that causes this packet to warm up. It can be held in one's hands to keep them warm on a cold day. Finally, as an example of an endothermic chemical reaction, we look at the photosynthesis process. This is a sketch of the cross-section of a leaf of a tree. Inside of the leaf, sunlight is absorbed and used to drive an endothermic chemical reaction that converts CO2 into a fuel that the tree can use to survive. And of course, oxygen is a byproduct of the upgrading of the CO2. A third example is the deceleration and absorption of neutrons in the fuel element of a nuclear reactor. Here we have a conversion of nuclear energy into thermal energy. The picture on the left is that of a fuel rod unit. Nuclear fuel is contained in the cylindrical elements in the fuel unit. One often can represent the nuclear fuel element as a cylinder or sometimes a plane wall, and often there is a cladding on the element. Here the cladding is steel. Due to the conversion of nuclear energy into thermal energy within the fuel element, this thermal energy must be transferred away from the fuel element to prevent it from overheating. As a final example of a problem that includes volumetric thermal energy generation and is often modeled as steady state and one-dimensional, consider the absorption of light in a semi-transparent medium. In this picture, we see a solar chemical reactor. Here we are looking at the reactor after the sunlight has been turned off. The reactor remains hot and is radiating energy out, which is why it appears to be bright on the inside. This reactor includes a quartz window. If you were to look at the radiation passing through the window, some of the visible light, for example the sunlight, passes straight through the window. This is called transmitted sunlight. But some of the sunlight is actually absorbed within the window itself. This is a volumetric phenomena. It happens within the domain of interest, which is the window, and could thus be treated using steady-state one-dimensional heat transfer with constant properties and with thermal energy generation included. To develop a technique to analyze problems in this category, let's consider the example of a planar nuclear fuel element. To be planar means that the system is Cartesian. It is like a plane wall. Due to nuclear decay, thermal energy is generated within the element. An engineer may ask the question, what is the temperature on the inside of the fuel element in steady-state operation? It would be important to keep the fuel element at a safe operating temperature. If it overheats, it could melt. Here we see a sketch of the fuel element. It has an overall thickness of 2 times L. Here we are using the variable L to denote the half thickness of the element. We will assume that there is a flow of cooling water that maintains the surface temperature of the fuel element at a temperature denoted by T sub S. Before we begin to analyze this problem, let's make a guess. What do you think the distribution of temperature inside of the fuel element is? Sketch your guess on axes like those below. Now, what I would like you to do is pause the video and write down an answer to the question. Have you sketched a guess for what the temperature distribution may look like? Note that the temperature must start at Ts at x equal minus L, and it must also end at Ts at x equal L. What does the temperature look like between those 2 points? If you have not made your sketch, please pause the video and do so now. While any guess is acceptable, it is, after all, just a guess. Here is one possibility. Perhaps your sketch looks something like that of my own. I imagine that the generation of thermal energy within the fuel element causes the temperature on the inside of the fuel element to be greater than that at the surface. One may not expect it to be linear in this case. Maybe one did. We will find out. One thing to note, regardless of your sketch, is that because the surface temperature is the same on both sides of the fuel element, we can expect the distribution of temperature, whatever it may look like, to be symmetric. To be symmetric means the problem is the same on both sides. To the left of the y-axis, to the left of the temperature axis, the shape of the curve is identical to that on the right side of the temperature axis. Since the temperature distribution is symmetric in this problem, and that is important to note, this symmetric distribution is unique to this problem, and not all problems include a symmetric temperature distribution, but it is advantageous if you can identify symmetry, because the following statement will always be true. Since we know that heat transfer is by conduction inside of the fuel element, then we can apply Fourier's law. If we apply Fourier's law at x equals 0, which is in the center line of the fuel element, here, the point of symmetry, the mirror point, Fourier's law says that the flux at this location is equal to minus times the thermal conductivity times the gradient of temperature at that location. Due to the symmetry, however, the gradient must be 0. The slope of the temperature distribution is horizontal at this location. Consequently, Fourier's law predicts that the heat flux is at the center of the element is 0. There is no net transfer of energy across the center line of the fuel element. This is an important observation to make that greatly simplifies the analysis of the problem. You should always be looking for symmetry locations in problems that you are analyzing. Now that we have identified a symmetry plane, let's analyze a control volume on half of the fuel element. I've drawn the boundaries of the control volume with a dashed purple line. Here I've drawn it away from the sketch so that we can focus on the heat transfers across the surfaces and on conditions on the inside of the volume. First, we note that there is generation of thermal energy within the control volume due to the decay of nuclear material. We have identified that the control surface that is coincident with the center line, there is no heat transfer at this location. The conduction heat transfer must be 0 because the control surface is aligned with the symmetry plane. On the other control surface, however, there must be conduction heat transfer, because energy must transfer out of the fuel element into the surrounding water. I have drawn the control surfaces just on the inside of the fuel element so that it exposes conduction heat transfer at this face. Let's now apply the heat transfer energy balance equation. The heat transfer energy balance equation says that the rate at which thermal energy is stored within the volume must be equal to the rate at which it is transferred in minus the rate at which it is transferred out plus the net rate at which it is generated within the volume. We of course have no storage because we are dealing with a steady state problem. So this first term goes to 0. I see no energy transferring in because we have identified that there is no heat transfer across the symmetry plane. There is a transfer of energy out by conduction, and there is thermal energy generation within the volume. Solving this, we see that the heat transfer energy balance equation on this finite volume tells us that the rate of thermal energy generation within the fuel element must equal the rate at which that energy is transferred out of the fuel element at its surface. Note that the rate of heat transfer is not a constant in the x direction. The rate of heat transfer at x equals 0 is 0. This is a symmetry plane, but we have just identified that the rate of heat transfer at x equal L at the surface of the fuel element is not 0. We thus must conclude that the rate of heat transfer is not a constant throughout the cross-section of the fuel element. This is a result of the thermal energy generation within the volume. Because the rate of heat transfer is not a constant in the x direction, the temperature distribution cannot be linear, and we thus cannot apply the thermal circuit idea from Lesson 7. This is a fundamental idea to understand. In the presence of thermal energy generation, the thermal circuit analogy and modeling does not apply. This will always be true in problems that include thermal energy generation. In order to continue, we need to develop an equation for the temperature distribution. This requires a new form of analysis, and this new form of analysis is the focus of the next part of the lesson.